using real chemistry moles. And I've got examples of chemical moles that we'll go over. And let's see, what's the best one to start with? Let me switch over to just a quick camera view. And let's see, camera. I'm going to get to the HD camera. And you'll see that I've got one substance here. I'm not sure if you can make out, it's got the letter C on it. It says for carbon. And then this one, I'm barely lifting up. This has got W tungsten. And then here we've got, I should have put the carbon next to it because it's the diamonds that I've got. And then here I've got a little bit of sodium chloride, some salt, a salt crystal, a pretty salt crystal. So we've got sodium chloride, we've got carbon in the form of, oops, let me move it over, diamonds, we've got carbon in the form of graphite, and this stuff, yeah, man, that is unbelievably dense, within a couple of percent of the densest element that you can get. So we've got two elements and a compound, and that's the sodium chloride. I've got two of them listed here. One is carbon and one is tungsten. So I'm going to start by taking out this carbon. Okay, in fact, I'll go to the wide view because you've had the close-up. Here, go to wide view. Welcome to the moles. And let me prop this open and pull out this cube of tungsten. I'll turn the balance on and check out the balance. I'll turn it so I can see it better. It's 317 grams. Okay, we get a reading, you write it down, and I've got my W, tungsten. The other name for it is wolfram, and I have 317 grams. That's, 500 grams is pretty close to a pound. So, like I say, a cube that's 1 inch like that, you're not going to get with anything else that's, I know, gold's the same density. The only other two things are iridium and osmium, and I'm not going to be able to afford the iridium or the osmium. So here we've got super, super dense. 1 cubic inch is 317 grams. And I'm going to switch over to here to this. It's just sort of a black cube. It's soft. It's graphite. It's the same stuff that's in your pencil, except your pencil is mixed in with clay. And this one's only 31 grams. 110. Oh, yeah, almost exactly 110. 31 grams of carbon. By the way, my diamonds here are 31 grams too. In fact, if you sort of notice, the diamonds take up a little bit less space than the graphite because the diamonds are basically just compressed graphite. And I'll put the graphite back into its little cube because it's soft, it'll scratch easily. In fact, actually, here, let me get my paper out. As I say, this is the same stuff that you have in pens, and I'm not sure. There, I rubbed some of this off on the paper, and it left a mark, just like a pencil. The pencil has some clay mixed in with that, and that clay mixture is your number 2 pencils that a famous American writer ended up producing the best pencils in the United States. Okay. Now, here's the question. Of the, we'll get the sodium chloride out of the way. Of these two things, wow, this tungsten is unbelievably heavy. And this is super light. Of these two, which do I have more of? This stuff. Like I say, if I threw the graphite at you, because it only is 31 grams of mass, it would just bounce off your head. But the tungsten, I mean, they use tungsten as anti-tank weapons, tungsten projectiles, and because they are so dense. So the massive part, tungsten, wins by the mile. In terms of volume, both of these have the same volume. We talked about a density comparison too, but the one we've got to get to next is moles. And right here is something that you should always have nearby. Let's see. You might be able to see it. It is the periodic table that's used with AP exam. This is exactly the one you have on AP exam. Use this one only. I mean, there's some really nice periodic tables. I've got one here with my lab notebook. I'm going to pull out. It's colorful and pretty and everything else, but I just use this. My lab notebook has got in fact, I've been taking my data down and I use this as the backer because it's got when I write on it, it makes a copy. They refer to them as carbon copies, but that's another story. And this is where we're going to come to the moles. The atomic weight, carbon, 12.01. And my next question is, there's a unit for this, has an atomic weight of 183 W. W is way down there in the transition metals, close to gold. And there it is, 183.84. And I wrote the number down, but I need a unit. I'll leave my periodic table right here. What's the unit for atomic weight? You know, if I was going to say any one would be forced for a right answer, I would say right now AMUs if I had to write this down. But it is also grams per mole, because the way we're running this for AP is that we're going to say if you have 1 mole of this, it is going to weigh 12.0 grams. Now that mole is a certain number of atoms, 6.02 times 10 to the 23. The number is sort of irrelevant. I mean, it changes a little bit depending on how you define it. It's just a heck of a lot of atoms. So if you have 12 grams of carbon, you have 1 mole, but we have 31 grams. So if I want to change this into moles, I would go 31 grams. I only had the 2 significant digits times, this is my ratio, grams on the bottom, which is a defined 1, and 12 point, oh, no, wrong. It's 12.01 grams per 1 mole. So it's going to be 31 divided by 12, and that makes sense. You know, if 12 is 1, 31 is going to be about not quite 3. In fact, it turns out to be 2.538. Oops, let me get out of the way. Oh, wait a second. I've only got 2 significant digits there. So 2.5 moles. For the accuracy I weighted at, I have 2.5 times 6 times 10 to the 23 atoms, because this was an element. So notice I wrote here amount. For a chemist, moles are the amount that we like to look at things with, because the atoms are the things that do the reacting. Now, we don't care if you can put a dent in somebody's head with this tungsten. We care about how is this tungsten going to react chemically, and it reacts by atoms. So the moles are very, very important. In fact, in any problem, if they give you a weight and a substance, change it to moles. You're going to have to do it. They wouldn't have put that weight in there and that formula unless you had to change the moles. So you'll be doing this hundreds of times. And I'll do the same thing with this. Now, this is 317, 183. So about 1.5. I did the division earlier. 1.7 moles. The original question. Volume-wise, they're the same. Weight-wise, tungsten wins by a mile. Number-wise, carbon, the graphite, and of course, if you prefer diamonds, win by the mile. In fact, you can do a density in terms of how many moles per cubic centimeter, or how many moles per liter rather than grams per liter, and you'll find that graphite and diamonds, in terms of elements, are like the densest materials known. One of the reasons diamond is such a good conductor of heat, and also is very strong, is because it has the most number of atoms packed into the smallest possible space. We can explain a lot of things using moles that we can't explain using grams. Here's an analogy. Oh, let me turn this on. 189 grams of marbles, roughly. Don't forget the size of this. 189 grams of marbles. 189 grams of ball bearings. The weight's the same, but if I'm throwing things, I can have a lot more marbles to throw than ball bearings. Now, the ball bearings will be heavier because of the mass, but still, I've got more marbles in 31 grams than I have ball bearings. That's our moles. So how do we change grams into moles? Well, of course, we divide by the atomic weight, and we'll deal with compounds later. Why? And that's the big thing. Chemists worry about reactions. And what does the reacting? The little particles, the marbles. And the more marbles you got, the more reaction you get. One of the reasons the lithium batteries are so spectacular nowadays is because the atomic weight of lithium is very low. So you can get a lot of atoms providing a lot of electricity for you in a relatively low weight.